Hello, I'm Alex Bolboacă from Mosaic Work Studios, and today we will look at techniques for refactoring legacy code through pure functions. So what we will look at is one specific idea that I discussed previously in a video with Adrian Bolboacă, which is that we can refactor legacy code by first extracting pure functions through very safe refactorings, then writing the data-driven tests or property-based tests on those pure functions, and then deciding whether to refactor the pure functions into classes or keeping them as they are. In this video we'll look at a few techniques for doing these refactorings, and the video will be followed by another longer one where we'll look at a full codecast of refactoring for a piece of code. The techniques we'll look at is how to extract pure functions, how to deal with state, and how to group pure functions back into classes. Enjoy! So the first technique we will look at is the basic technique for extracting a pure function, for actually starting the process towards pure functions. We will see that it applies on any level in code. You can pick an existing function, you can pick a block of code, you can pick a few lines of code, extract them, make the new function static, and this will tell you what the dependencies are, and then push the dependencies as parameters. As we will see, this does not always make a fully pure function. What you end up with may be a function that's static, but it still does some state changes. But we will not discuss about those for now. Let's see the technique in action, and then we'll see how we can move forward. So first thing we notice is when we go to this function, create row question, this it can already be made static. In this case it also happens to be a pure function, because by definition, so it matches the definition. If you pass in a different input value, you will get different output. You get the same outputs for the same inputs. We also have this method, displayable, that's not used at this point, but we'll leave it as it is. Now let's look at another level. Let's say we want to pick this part and just say something happens if the current player is in penalty box and there's an even roll. We don't know how to call this, but it happens player penalty box and even roll, right? And what we need to do now is to try to make this static, and we already see in red all the dependencies for this function. The easiest thing we could do is to add some of these things as parameters, and this leaves us with only one line of code that's not pure. Now the easy way to deal with this is by extracting an even smaller function from this from the other lines of code. We will see how to deal with state in a future technique. So I don't know exactly what happens here, just call it something. And now what we see is there are still some changes here, but this function can be static, this one cannot be static, at least not for now. So now I can inline this and I'm left with one function that is static. It receives all the parameters it needs. So it's one step further towards pure functions. It's not yet a pure function, but it's closer to this. Let's see this technique in other situations. So for example, in this case, if you look at this code, you can say, yeah, we can probably already try to make this static, but I don't want to do this because I may break some of the existing code. So instead I will do exactly the same thing. Extract, let's say current category pure. Try to make this static. It will tell me what it needs. Introduces parameter. Introduces parameter. And now it can be made static. Now if we want, we can inline this. Okay. Inline doesn't work because this interrupts the return statements interrupt the execution flow. But basically what we can do is actually inline current category. And as you can see now, this is calling the pure method instead. And in this case, this is a pure method because it doesn't change anything inside this. It's still not perfect because it reuses places of player multiple times. There's a repetition there, it's duplication. We can remove the duplication at a later time. But again, for what we need in terms of technique, you can see that it's fundamentally working. Let's see another area of the code. Now let's take this part. Answer something. Right. Again, try to make it static. Once again, we can introduce parameters. And in this case, what we obtain is a function that is not yet pure, and it also changes some things here. So we need to pay attention because in this case there's a state change. We'll need to make certain that this doesn't actually lead to any problems in our code. Okay, so this is the fundamental technique for extracting a function and taking it towards being pure. And we'll see other techniques. Now we will look at a technique for separating input-output from our code. And we start from the basic technique for extracting pure function. And the next step will be to separate that pure function from any input-output. We'll not look at any other state changes, just that input-output. And in order to make this, let's pick this function, for example. Add pure. Okay. So we see now that this is just calling it pure. This of course is not pure. We'll make it static. We can see that we need players, places, nurses in penalty box. We can inject some of these. But before we do that, we also see that we have to print statements. So how can we deal with these statements instead of just having them here. The simple thing we could do that uses functional constructs is to extract this as a function, print player was added, and then what I would like to do is make this static. This can be made static, right? And now I would like to introduce this as a lambda expression instead. And in order to do that, I will first initialize lambda from, and then replace this with the lambda. And now introduce this as parameter. And now what we've done is we've replaced our print statement with a lambda that is injected into our function. We can do even better, because what we would like to have is no player name. So instead of doing this, we can do a partial application. Remove this. And now this one can be introduced as a parameter. You see that the partial application has moved in the function call. And we are now using a lambda that whenever you want to test something like this, you can replace the lambda with something else. It can be any function that does nothing, for example. And or some kind of mock that will verify that this function is called. And this is the fundamental technique for getting rid of input-output, or at least making it very obvious where input-output is injected into as a dependency into our functions. We can do the same for the second one. Let's see, let's extract the function, print player number. Okay. Once again, I'm pushing this as a parameter. Okay, rename this. It's static. I can now create my function. I can replace this with this. I can inject this as a parameter. And I just separated myself from any input-output in this function. So once again, this is a simple technique where we extract the function, we look at the code, we see whatever is related to input-output, extract it as a lambda parameter, and then we can move on with making the function static and all the other things. The next technique we will look at is a way of extracting and injecting lambdas into a function. This works especially well when you have more complex code inside the initial function. So let's say you extract a bunch of code into a method. You try to make it pure, but you cannot easily do that because there are too many things to do. So then one way of dealing with this is by extracting smaller functions and then injecting them as lambda parameters. So let's see this in action. we'll take this part of the code. I don't care exactly what it does, I'll just call it something. And now if I'm trying to make this static, we've already seen that we need to inject a number of parameters. What I'd like to do is, I notice that there is some logic here. I don't exactly know what the logic is. I'd like to extract this as another function and just show you the fundamental technique. So if we make this static, we need to introduce places as a parameter. We need to introduce current player as the parameter. We can make some renames just to have this cleaner. And we now have a perfectly fine static method, which is not pure because it changes state. However, what we can do now is to turn this into a lambda parameter that we pass in. So we could, we notice, this is important, we notice that role places current player, they are not changed in the previous line. So what this means is that we can bind this to all its parameters. So we can create something else, lambda, that does, precisely this. And then this becomes something else, lambda. And now we can inject this as a parameter. And now if we look at the call to something, we see that the parameter has moved here. So the nice thing about this technique is that we can extract small parts of the code whenever we know that the parameters are not changed, and extract them into smaller functions and do this again and again as much as we need to. I have to stress again the fact that you need to make sure that the parameters don't change, because if you do the binding to parameters at this time, these values will probably be used depending on your programming language. And then when you go here, if you change the variables in the meantime, you might have surprises. But other than that, this is one fundamental technique that you can use to take a larger function, split it into small functions, and make the dependencies explicit by injecting lambdas instead of classes or data parameters. The next technique we'll look at is how to deal with state change. In order to make a function pure, we not only need to inject all the dependencies, but we also need to extract any state changes outside of the functions. So pure functions have to return a value rather than make state changes inside the function. Now, we can have state changes inside the function as long as they are local and they do not propagate outside it. But usually we can change the function to something that's pure, doesn't have any state changes inside of it. In order to get there, what we need to do is to extract functions to store the initial value before the state change, to make the changes, and then to store the final value, and that final value becomes the return value of the function. And let's see how we can do this with an example. We will now look at extracting these two lines of code. As you can see, they are making some state changes, and we can now see the technique in action. We start by extracting this, do something with current player, and the first thing we notice is that there are state changes here. So now let's extract current player as a different variable. As you can see, this is not a clean refactoring. It doesn't do precisely what it should do. We need to add one more line, current player equals player. We could see that it's a problem because this variable was not used anymore, this set. So now we can separate visually the part of the code that makes changes from the part of the code that, so this is actually a function that can have a return value, while this is just setting the initial state, setting the final state. And if we extract this, do something pure with current player, we can see now that this function is pure. Can make this static. Let's inject, instead of injecting players, let's now inject players.size as a parameter, because this is the full expression of what's used. Let's add the return statement for clarity. And now we see that this is modified, but all the changes are local. So what we can do is to inline in reverse order. So current player equals this function call, this player, we inline it. So now we have current player do something pure with current player, which receives the current player and something else. And we can inline this as well. And this has now replaced our state change with a pure function that makes no changes in the global state and returns a value that then can be stored in the global state if we want to. If we look at this code, we can also change it. First of all, this statement, we can simply refactor it if we add an else statement. So what happens? If players is size, player is 0, else player equals player, which is a silly assignment. Actually, it even tells me it's a silly assignment. But the nice thing about adding it is that we can replace this with an expression. I like to have parentheses here. And now normally I would inline, but it doesn't work. So what I can do is inline manually. So now we have this as an expression. It has this, if player is size, returns 0, else it returns player. And we see that this is actually an assignment that's local, an increment that's local. So one thing we can do is to replace this with the increment. So the general idea would be this. And we can leave it like this, or we can change our code. But now we can make this final, we can make this final, and we see that there is absolutely no change in the code. So again, this is a very simple technique for separating state out of a pure function. Basically what I did was extract a function, identify the areas where there was a change, introduce a local variable that's used instead of the global variable, set the initial value, set the final value, transform the body into a function, and that function becomes something that changes the value and returns. It doesn't actually change, but it returns the new value for the variable. And if you know more about functional programming, this is basically similar with refactoring towards a state monad. If you don't worry about it. It's a very simple technique to understand. Now, the nice thing about this is that this function now is very predictable. We can see precisely where state changes happen. They are very separated from the points where there is immutable code. And this is the kind of thing we are looking at. We want to separate immutable code from mutable code. This time we will look at our final refactoring technique. We are now at the moment where we've refactored toward pure functions, and we would like to move these pure functions into classes. We don't have to do this, but this is usually one of the steps we'll take in the end. In order to do that, we will look at pure functions that have similar parameters and think about the cohesion between these functions. And we would like to obtain classes that have cohesive functions. That means they act towards the same goal, which means that we will introduce these functions, extract their parameters as data members, and then introduce a constructor, which means we will have a class. Let's see an example. This time we will look at Java code. This is code that Adrian Bolboacă refactored in one of his remote pairing sessions. And we already have a few functions here that have similar signatures. So you can see that we have print function player number, print function player name, player number, player name. There are various options for structuring this class, so we could make a class that contains all the 4 functions, or as I would like to do, I'd like to have smaller classes that have pure functions. And let's look, for example, at write player number edit. We have another one which is create player number message. So what I will do is I will group these 2 functions into a class. First step is to move members to a new class. We want the new class to be in the same namespace as the others, and we will name it for now player number printer. And we want to move 2 functions, write player number edit and create player number message. We just allow IntelliJ to do the change for us. And now what we'd like to do is to make these 2 functions members. What this means is we see there are a few things that are repeating here as parameters. These should become data members in our class. So first we can say bind method parameters here. But then instead of doing this, what we'd like to do is to remove the static. Remove this. Add constructor parameters. We'd like both of these to become constructing, initialized in constructor. We'll just keep the data members on top. Now, as we can see, these are not used, but we can simply eliminate this, eliminate this, eliminate this, make this non-static. I also know that this function create player number message is only used here. Make it private. And now if I'm going here, what I need is a new player number writer of these things. And then eliminate these things. And now we have a new class. Let's look for a moment at this class. It's called player number printer. It's something that prints the player number. It does two things. It formats a message and it actually prints it. But it does so through dependency injection. So the print function is injected and the actual value of the player number is also injected here. As I said, there are various ways of structuring this design, but this is a very simple example that shows how you can move from pure functions to a class. So just to say it again, we look at functions that have similar parameters. Those parameters become data members, and then functions becomes a method that uses the data members instead of receiving all the parameters. And this is, in a nutshell, we can say that every method in a class is a pure function that's partially applied to the data members of that class. And that's how this refactoring works.
Coming next.
When not to use BDD, when is it not very useful?
And I wish I could say it's useful everywhere, all the time, but that would be a lie. This is not a new silver bullet. BDD is useful when you have a reasonable understood domain. It's not usable when you have a domain where you're exploring, where you don't know what you're doing, when you're discovering things. Then that's not the point in time to use tools like BDD.